In this video, we're going to discuss some properties of limits and introduce the notion of continuous function and show how they're related. We've been using these properties of limits implicitly. We haven't even stated when we're using them. It's always seemed a correct and plausible use of them. Now I want to make it explicit some of the things we've been doing. I'm not going to do a formal proof of these properties yet. We'll do that further down the road. Most of what we're going to be doing in this basic course, you can get by with just an intuitive knowledge of what a limit means, and that's what we've been doing so far. But again, let's make it explicit, some of the things some of the properties of limits we've been using. But let's start with the notion of continuous function. All right. The definition of a continuous function is the following. Well, let's first look at a function that's not continuous. That's the easiest way to see why the definition makes sense. So this red graph is a function of a discontinuous, is a graph of a discontinuous function. And it's discontinuous at only one point, at the point x equals 2. Every place else the graph is continuous, and you can see that from the fact that the graph isn't broken. So graphically, continuity means the graph is not broken. The formal definition is the following, and you always state the definition at a particular point. So for instance, we would say g of x is continuous at x equals 2 if the following three conditions are met. First of all, g has to be defined at the point we're talking about. So g of 2 has to be defined. And the upper limit has to equal g of 2. And the lower limit has to equal g of 2. Notice the difference between these two formulas. This one has a plus h in there. This has a minus h in there. And we're going to be assuming that h is positive. So what does that mean graphically? Well, look over here. g2 of minus h is this number down here. And g2 of plus h is this number up here. And right now I have h set to 1. Watch what happens to those 2 points as I make h smaller and smaller. They're both converging. They're both converging to something. But it's not g of 2. g of 2 is the point in the middle here. g of 2 is this point right here. So the upper and lower limits are converging, but they're not converging to g of 2. So for that reason, we say that this function is not continuous at the point x equals 2. And let's look over here and see the numerical counterpart of what's going on in the graph. This one is, roughly speaking, the upper limit. It's not the upper limit yet because we haven't pushed h close enough to 0. And this one down here is the lower limit, or it's approaching the lower limit. It's not there yet. And this one in the middle is the value of g of 2. Clearly they're not the same. But let's make h even smaller and watch the upper and lower limits. They will eventually approach numbers. They're not, if we looked at more decimal places, they wouldn't be at 6 and 2, but we can get them as close to 6 and 2 as we want by making h smaller and smaller. So if we want to make this function continuous, we have to get rid of the gap. And we can do that in this case by just making this gap 0. Now the function's continuous, and notice over here, our upper limit, our function evaluated at 2, and our lower limit are all the same, or expressing it in a slightly different way. A limit as h goes to 0 from above equals g of 2, and the limit as h goes to 0 from below is g of 2. So these are all expressing the same thing, the fact that this function is continuous. Now let's contrast that with something else that we've looked at. Let's compare that to this function, sine of h over h. We saw that that limit exists, and in fact the limit as h goes to 0 we saw is 1. Let's ask ourselves the question, is this a continuous function? And the answer is no, it's not continuous because the first condition isn't met. G of 0 is not defined. If you plug a 0 into this formula, the denominator becomes 0 and division by 0 is not allowed. We go over here to our numerical evaluations, we see that the computer kicks out a nan, which means not a number. So this is not continuous, even though the limits exist. Now, where we've sort of used this fact of continuity is in a situation like this. Let's remember in one of our proofs we had a formula that looked like this: 1 over 1 plus cosine of h, and we want to know what the limit of this was as h went to 0. Well, this is a continuous function at h equals 0. Let me plug it in here and see if it what the graph looks like. Just let's see if it comes out right. 1 plus the cosine of h. Okay, well there's our graph, and it certainly looks continuous at 0. And is it defined at 0? Yeah, it is. There's no problem with putting an h equals 0 in here because the cosine of 0 is 1, and 1 plus 1 is 2. So this thing evaluated at h equals 0 is 1 over 2, or 1/2. And so if we approach the limit, that's going to be the limit, because that's the property of continuous functions. As we let h get smaller and smaller, if it's continuous at that when h equals 0, then those upper and lower limits have to converge. And over here we see the same thing. So in fact, to evaluate this limit when the function is continuous, all we need to do is plug in the value h equals 0. So that makes life very simple. Contrast that with our situation here, where we can't evaluate this limit by just plugging in h equals 0. We had to use an argument involving, remember, the 3 areas that were a little one, a middle-sized one, and a big one. And we showed that, took those areas and then showed how you can prove that this function sine of h over h is sandwiched between 2 continuous functions, each one approaching 1 as h goes to 0. So it's a lot more complicated when your function is not continuous. All right, so that's one property that we were using implicitly, the fact that we can just substitute h equals 0 when we're dealing with a continuous function. The other property that we've been using implicitly without really worrying too much about is the following. Consider this function here, g of h. So g of h is defined as the product of 2 different functions. It's this one and this one. Now each of those has a limit, and in our proof of the derivative of sine of x equals cosine of x, we just assume that the product of the 2 functions will approach the product of the limits as h goes to 0. And we never really proved that, but it certainly seems plausible. Now we're going to give some indication of why that might be true in general. Before we do that, though, let's just look at the graph of this product. The graph is the red function above. And let's first ask the question, is g continuous at x equals 0? Well, we first have to ask the question, is g defined at 0? And the answer is no, because this part of it is not defined at 0. We have a gap in our graph just as we did before. And if we ask the computer to evaluate g at 0, we get the same result. We get nan, not a number. This is not continuous, so we can't just plug in h equals 0 to get this limit. But what we can do is take the limit of each one individually and then take the product of those two things, and we get the limit of g of h. Now up here I've written down the limits. Limit 1 is the limit of sine h over h, and limit 2 is the limit of 1 over 1 plus the cosine of h. So how would we prove this? Well, first of all, let me generalize my functions a little bit so that our proof will apply to any situations, similar situation. So let's call our two functions p of h and q of h. So what we want to show now is that if we look at g of h minus the product of the limbs, lim 1 times lim 2, as h gets closer and closer to 0, this thing should go to 0. And right now h is 1, so that's not real close to 0, but I can make it close to 0 by, again, making h as small as I want. So right now we're like, the difference between is roughly 1/10,000,000th. So they are very close together. Now how will we prove that, or make it a little more plausible? Well, we're going to use a trick or technique that you see in other proofs. So even if you think we don't need it, that you're convinced that this is true in this case, this technique is worth knowing. So here's the technique. Let's big this thing. And the first thing we're going to do is use our definition of g of h. That's the product of two things. So let's make that explicit. G of h is a product of p times q. And now here's our trick. Here's our technique. We're going to look at the first grouping. It's this, the first term of this difference is this, and the second term. And we're going to take a little piece from this and a little piece from that and add it to the formula. But that's going to change the formula, so then we're going to subtract it off again. And we do that because, well, you'll just have to wait and see. So let's do that. We're going to subtract off p of h, times, now I'm going to take something from the back end, and I'm going to take lim 2. And of course that changes my formula. My formula used to evaluate to 0 essentially. This is very close to 0. Actually, let me make my h back to 1 just so we can do a numerical check a little easier. Our original formula was 0.0463. Now I've added something in, so of course I got something different. But I can subtract that same thing out again. So I'll just copy this over, or actually I've subtracted it, now I'm going to add it. So I do a plus and repeat the same thing, and now I'm back where I started from. Well, what's the point of that? Well, let's do some grouping. Let's group the first two things together. So I do a Control G, and the last two things together. Control G. Now I note that I have a pH and a pH in the two terms of the first grouping, and a lim 2 and a lim 2 in the second, in the two terms of the second grouping. So if I do a factor all terms, I'm going to factor those common things out. All right, now look at our pieces here. Lim 2 is a number. In fact, in our case, it's 0.5. It's this up here. In the more general case, we don't know what it is, but it's always going to be a number because we're assuming both these limits exist. That's the assumption we're making to start out with. So this first piece then is something that's approaching 0. This piece here this piece right here That's going to 0 because lim1 is the limit of p of h as h goes to 0. So, watch it, just a numerical confirmation. Let's make my h smaller and smaller. That's going to 0, and therefore this whole thing, since it's a very small number times 1/2, that's going to go to 0 also as I make h smaller and smaller. So one piece of this sum goes to 0. Let's look at this side here. We can say the same thing about this piece here. Remember, lim2 is the limit of q of h as h goes to 0. So that's very small already because h is small, but I can make it even smaller by making h small. Now if I multiply that by p of h, I don't know exactly what I have because p of h is changing. As h varies, p of h is changing. But I know that p of h is bounded. Let me go back and remind you what p of h is. P of h is sine of h over h. And if I look back at my graph of that function, this is p of h here. Certainly bounded. In fact, it's bounded by, 2 would be a bound, or 1.5 would be a bound, or 1.15 would be a bound, or a million would be a bound. Doesn't matter what the bound is, it's constant. So we know then that this total expression here has got to be some very small number times some other bounded number. So that has to go to 0 too. And let me go back to okay, see right now it's not 0 because my h is, I put it back to 1, but I can certainly make it 0 by making, or make it close to 0 by making h small. So it doesn't matter what this pH is, we know there's a bound for it, and this part's going to 0, so the whole thing goes to 0. Well, since the two pieces go to 0, the whole thing will go to 0. So that's our justification for assuming that as h goes to 0, this product here, goes to the product of the two limits. Okay, we'll say more about this when we get to a formal proof of continuity and a formal proof of limit. I don't want to do that now because, as I hope you can see, we can certainly get by with our intuition to a large extent, and eventually we can prove these things. But I've known people who started out studying mathematics and they ran up against the formal definition of continuity and they decided to go into marketing or some other field. So the formal definition is a little daunting unless it's presented the right way, but we'll get around to that